Hello, this is video 55. I'm going to be talking about rotational kinematics. So we're going to be looking at the kinematic equations that we know and love and see how they work when we're talking about rotating objects. So before we can discuss the kinematic equations, I just want to mention this topic here about the relationship between rotational and translational quantities. So first of all, translational here, this just means linear, all right? And we've been talking about how distance becomes an angle, how linear speed or translational speed becomes an angular speed omega, how linear acceleration or translational acceleration becomes an angular acceleration alpha. So it turns out that there's definitely a relationship between the linear and the rotational quantities, because for example, if you're rotating something, so it has an angular velocity omega, well, you know that a point on the edge here, right, the faster that you rotate, the faster the omega, the faster that linear speed v. You know there's a relationship between the two. So we're going to look at that relationship very briefly. So the relationship between the linear distance s, which was that arc length, right, when you travel a certain angle theta, then this is the arc length s, and this was theta over here. So the relationship between the arc length and theta was already described when we talked about the definition of the radian, and we used s over r for that angle. So we're not really going to use this one much, but it does come into the derivation of the other two relationships that we're going to use. So if you use that your speed is your distance per time, use the relation that we just found for the arc length, that distance, and then the theta divided by time becomes omega, and we now get r omega. Very similarly for the acceleration, which is a change in v over t, well, v we just saw was r omega. You plug that in, and then omega over t becomes alpha, so we have r alpha. Again, I'm not too big on derivations on this class. I just wanted to show you that these equations weren't coming out of nowhere, that they're not too hard to derive, but we're just going to be using the relationships. So v is r omega and a is r alpha. So what this is telling us, if we look at the example with the velocities here, is that if we're trying to find that linear speed v, it depends on omega and it depends on the radius, how far away that you are from the axis of rotation. So we talked about that a point far away moves faster than a point closer. Well, how much faster? This relationship tells us, right? If the radius is twice as big, then that means that linear speed is going to be twice as big. So this really tells us the relationship. So just a reminder that every point on a rotating object has the same angular motion, but it does not have the same linear motion. As you can see, because the linear motion depends on the radius, how far away you are from the axis of rotation. So let's look at a question. It's very similar to one that we saw in the previous video. Rashid and Sophia are riding on the merry-go-round, but this time it's asking about how does Sophia's speed compare to that of Rashid, and Sophia is twice as far. So when it just says speed, it's talking about the linear speed or the translational speed, which is r omega. So they both have the same angular speed or angular velocity, but Sophia has twice the radius. So let's use VR, this is Rashid, and then the V for Sophia, well, she has twice the radius. So you can see that her speed is going to be twice that of Rashid. So now we're ready to talk about the kinematic equations. So maybe these look Greek to you. Well, they should, because they are using Greek letters. But what I really want to emphasize here is that we're just doing the same exact thing that we've been doing. But instead of seeing x in our kinematic equations, we're going to see theta. Instead of seeing v, we're going to see omega. And instead of seeing A, we're going to see alpha. So do you remember what this equation used to look like? It used to look like VF equals V initial plus AT. And now we just make these three substitutions. And so we have omega final equals omega initial plus alpha t. So how do we use this kinematic equation? The same way that we used it before, except that our variables are now different. So I rewrote the 5 variables here. Theta, omega initial, omega final, alpha, and t. These are my 5 variables that I like to use to describe motion. So if we know or are looking for omega initial, omega final, alpha, and or t, if we care about 3 of these and are looking for the 4th one of these variables, then this is the equation to use because it has all 4 of those variables. And then as you go through the kinematic equations, right, this one right over here used to look like delta x equals v initial t plus 1/2 at squared. That's what it used to look like. Well, now we have those substitutions. And if we care about theta, omega initial, alpha, and t, then this is the one to use. This equation does not have omega f, so we don't care about omega f. And then the third equation used to be 1/2 times v initial plus v final times t. Then the 4th equation used to look like v final squared equals v initial squared plus 2a delta x. So we use this last one if we don't care about t, since t doesn't show up in this equation.